In this video, we will learn different type of motion of the fluid particles when fluid is flowing through some flow field. We will also discuss the different type of deformations happens to those particles passing through different type of flow regime, having different type of velocity gradient. We will also discuss the conservation of mass, or sometimes we call it continuity equation, in this video. So let us start with first point, that is types of motion or corresponding deformation of fluid elements going through some flow field. So in this figure we have this fluid element which is shown with the help of some square, and for sake of simplicity we have taken only two-dimensional flow, and these lines are straight line, and in all the situation, like in this situation, in this situation, or in this situation, this situations, these lines remain straight because we are considering that this change is happening at very infinity small distance. So for that we can consider that their orientation may vary, but their straightness will remain same. So suppose this is the element of fluid which is passing through some flow field, and after certain time, let's say after delta t time, it takes this position which is shown with the help of this graph. So when it moves from this location to this location, in that case what happens, it may have these types of motion. It may have translation, it may have linear deformation, it may have rotation, or it may have angular deformation. Generally it may have combination of all these four. Now to distinguish what are these different motions and different deformation under different condition, let us first understand what is translation. Suppose if you have a flow field in which u, which is the velocity in x direction, it is function of x only. Sorry, it is function of, it is constant. If u is constant and v is the velocity in y direction is also constant. In this case what happens, suppose this is the element, after time delta t it will occupy this position. It will occupy this position because u is constant, v is constant. So this distance will be equal to u into t, and this distance will be equal to v into t, and it will have same position, means its angle will remain 90 degree and there will not be any deformation. So this is called pure translation. In this case there is no deformation. Fluid element is not subjected to any kind of deformation, and this is pure translation. And fluid is not subjected to any kind of strains because their size of the fluid element of different position remains same when it moves from one location to another location. Their size also remains same. Suppose let's say this size and this size is same, only the orientation is now different. Now we will consider the second aspect, that is about the linear deformation. Suppose we have a flow field in which u is function of x. It means that u varies in x direction, it means that we have velocity gradient in x direction, and v is function of y. If v is function of y, it means that we have velocity gradient in y direction. Because of that, what happens? For x direction, I have shown here with the help of this figure. This is the original element O, A, C, V. Now here the velocity is u. It is shown here with the help of u vector. And since velocity is function of x, so at a distance delta x, the velocity will be equal to what? With the help of Taylor's expansion series and removing the higher order term, with this approximation that delta x is very small, infinity small. So this will be u plus del u over del x, means gradient in x direction multiplied by distance in x direction. What is distance in x direction? It is equal to delta x. So means this point over the time, means after time t, after time delta t, this particle O, A, C, B occupies this position O, A dash, C dash, B. And this O to O is the movement which is equal to u multiplied by delta t. And A to A dash, from this A to A dash, this will be equal to u plus del u over del x into delta x velocity multiplied by corresponding time, which is equal to delta t. So this distance will be equal to what? This velocity u plus del u over del x into delta x multiplied by delta t, and this distance from this point to this point will be equal to u multiplied by delta t. Right, so it means that this A particle, A position of that particle will have position now A dash rather than A, because of this axis velocity at point A in comparison to O. So what is this axis distance? A to A dash will be equal to this axis velocity. Axis velocity was equal to del u over del x into delta x. So del u over del x into delta x multiplied by time delta t. Right. So with the help of this, we can find out the linear strain. Linear strain, if it is designated by epsilon xx in x direction, then this is equal to what? Change in length. Change in length is del u over del x multiplied by delta x multiplied by delta t. That is the change in distance or change in length divided by original length. Original length is delta x. This is the definition of the strain. So delta x is cancelled, and we can write this as epsilon xx rate, because this delta t may come here. So this is known as strain rate, linear strain rate in x direction is equal to del u over del x. Similarly, if we have the v component, because of the v, this point OB will travel this position. This additional distance may be calculated, and ultimately if we do same analysis as I have done here for finding out strain rate in x direction, we can get strain rate, linear strain rate in y direction, epsilon by y is equal to del v over del y. So in this manner, we can find out the strain rate in terms of the velocity gradient of u, v. Similarly, if we have a three-dimensional figure, which I have not taken, we can find out epsilon zz also. So let's think in another way, that what is the change in volume if there is only change in x displacement. Y magnitude del U over del x multiplied by delta x multiplied by delta t. So this is del U over del x multiplied by delta x multiplied by delta t. This is the net displacement multiplied by area. Area is delta y delta z. So this is the change in volume. Now if we want to know the volumetric strain through it, then volumetric strain is equal to d delta v divided by delta v, and if we want to write in terms of the volumetric strain rate, then divided by dt. Right, so if we take the limit as delta t tends to 0 because we want to write in differential format, then this is equal to del u over del x into delta t divided by delta t. So this is equal to del u over del x. Similarly, if we do for y direction, if we do for z direction also, right, in this case, what is the volumetric strain rate? That will be equal to linear strain rate in x direction. This is the linear strain rate in x direction, and linear strain rate may be written as in terms of the gradient, because this linear strain rate in x direction is equal to what? Through this we can see that linear strain rate in x direction can be written in the form of velocity gradient in x direction, that is equal to del u over del x. So here we have del u over del x plus del v over del y plus del w over del z, and in simple vector format it may be written as gradient of v. Right, so here we have learned that if we have velocity in x direction, y direction as function of x, and in y direction it is function of y, in that case we will have the linear strain rate in x direction and linear strain rate in y direction, and that is equivalent to the velocity gradient in x direction and velocity gradient in y direction. And we have also learned that what is the corresponding volumetric strain if element is subjected to different type of velocity gradient in x direction, y direction, z direction. Right. Now we shall discuss the next point, in which we have rotation. So here through this figure we can analyze it. So this is a particle O A C B having infinitely small size in x direction and y direction, as given here as delta x delta y. Delta x delta y signifies that these dimensions are of infinitely small order. So this is the original particle at time delta t, and in flow field after time delta t, what happens to this particle? This particle is deformed like this one. So in this case, if this angle is designated by delta v and corresponding displacement, this displacement is equal to delta psi. If this is delta psi, this is delta psi, this distance is delta psi, and this distance is equal to delta eta, and this corresponding angle is equal to delta alpha. Right. So now we can find out what is the corresponding angular deformation, or we can also find out what is the corresponding rotation by defining these two terms. So in this case, we have another figure here. In this figure, we want to explain this thing that suppose we have x coordinate here and we have a y coordinate here. So we are talking about two-dimensional Cartesian coordinate system, and only these are the two lines. Here I have shown 4 lines. Here I am showing only 2 lines of same particle. Line number 1, line number 2. At time t. At time t plus delta t. At time t plus delta t. These 2 lines occupy these position O, A dash, C dash, let's say. And we know these, we can find out these corresponding angle d alpha, d beta, and this distance is equal to what? And this distance is equal to what? Now this is possible in the case when u means velocity in x direction is function of x and y. What does it mean? It means that there is a velocity gradient in x direction of u and there is a velocity gradient of u in y direction also. Similarly, v is also function of x and y. V, velocity in y direction, is function of x and y. Because of this, what happens? At this point, what is this velocity? V. At this point, what is the velocity? Because v is function of x, so it will be v plus gradient in x direction del v over del x, because we are moving in x direction, multiplied by dx or delta x. Right. Because of this additional velocity, this point moves more distance, so it is moved by more distance, this distance. So in time delta t, this point occupies this distance. If we talk about this distance is equal to v into delta t, and this distance is equal to v plus del v over del x into delta x into delta t. So what is the difference here? This difference is equal to del v over del x into dx, or in some book you will find it is written as delta x, multiplied by time dt or delta t. Right. Similarly, this distance will be equal to what? So to understand this, let us consider the velocity here. This is equal to u, and what is this velocity here? This will be equal to u plus del u over del y multiplied by dy. So this distance is equal to this distance I am talking about. This will be equal to del u over del y multiplied by dy and dt. Now with the help of these distances, this distance and these distances, because this distance is equal to what? From this point to this point, since u is function of x and y both. So here this will be equal to, I am writing here, dx plus del u over del x into dx into dt. This we have learned in the previous example also, so I am not explaining this. Because of this additional distance, we will get linear strain in x direction. But right now our focus is to understand the shear strain or rate of rotation. Right. So with the help of this figure, we can find out delta xi, and we are representing this as delta xi. This distance is delta xi, and this distance is delta eta. So with the help of the figure, we can find out delta xi is equal to, I have just explained this to you, additional distance traveled by particle situated here at this location, this point, and that is because of additional velocity, and that additional velocity is equal to u plus del u over del y multiplied by delta y. So what is the distance traveled by this particle multiplied by delta t, and what is the velocity here at this location? It is u. So because of that, this will be u into delta t. So net difference is del u over del y multiplied by delta y delta t. So this is equal to, I just explained to you that this distance is equal to del u over del y multiplied by dy into delta t. Now when I am writing delta y or dy or delta t as dt, both have same meaning, that they are of infinity small order, and we want to write a differential equation. So we will use the definition of derivative, as in this case dt tends to 0. Similarly, we can find out delta eta, and this I explained, and that was equal to del v over del x into dx into dt. So this is equal to del v over del x into delta x into delta t. Now after knowing these two displacement, we can find out the rate of angular deformation in xy plane, because we are considering only two-dimensional flow, and that is happening in xy plane. So we define it like this: rate of angular deformation is limit delta t tends to 0, delta alpha plus delta beta divided by delta t. Now we have already calculated the distances. So distances we have calculated, like we have for delta beta, we have calculated this distance. So this distance divided by this distance with some simplification and neglecting the very higher order term, tan this, and since this angle is also very small, so tan theta becomes theta. Okay, so based on that, we can write out limit delta t tends to 0, and this will become alpha. What is alpha? Delta alpha, this angle. So this delta alpha is equal to this distance, which is equal to del v over del x into dx into dt divided by this distance, and where we are neglecting the higher order term, multiplied by dx dt etc. So this may be written as del eta over del x plus del xi divided by del y, and this whole is divided by delta t. So we have already calculated this delta eta, delta xi, so substitute here, and we get rate of angular deformation in xy plane as del v over del x plus del u over del y. So here we have written rate of angular deformation at xy plane. What is this? This is equal to basically shear strain rate, and many times we define it by gamma dot shear strain rate. And once we know the shear strain rate, then from here we can find out the corresponding shear stress also but right now our aim is only to find out different type of deformation without understanding the cause of that deformation. So similarly, if we have angular deformation in YZ plane, for that rate of angular deformation in YZ plane may be written as del W over del Y, where W is the velocity in Z direction. So del W over del Y represents velocity gradient of W in Y direction plus del V over del Z. What does this represent? Del V over del Z, velocity gradient of V means in Y direction with respect to Z. Means what is the velocity of V? Velocity gradient of V in Z direction. Similarly, if we have a ZX plane, then for that we write this as del W over del X plus del U over del Z. Right. So here we have learned how to relate for simple two-dimensional flow the rate of angular deformation to the corresponding velocity gradient. Now we shall discuss the fluid rotation. So first we will define the fluid rotation and then we will quantify it. So rate of rotation, or that is also termed as angular velocity at a point, is defined as average rotation rate of two initially perpendicular lines that intersect at that point. So basically in this case we have a point O, and here we have these two mutually perpendicular lines. So we will calculate the average rate of rotation of these two lines. This is line number 1, this is line number 2. Right. And so it means that average means 1 over 2. And since rotation is having certain sign also, so let's say we give positive sign to clockwise or anti-clockwise, in whatever sign convention we want to follow, you can follow. And we have to give corresponding rotation. So we have already calculated delta alpha and delta beta. What is delta alpha, delta beta? Delta alpha was this thing and delta beta was this thing, and ultimately by using the limit and definition of the derivative, this is delta alpha and this is delta beta. This portion is delta alpha and this portion is delta beta. Right. So as per this definition, we want to calculate the rate of rotation. So this is again written here for sake of completeness, but we have already calculated delta xi and delta eta, and based on that we have already calculated the theta. Theta means delta alpha and delta beta. So omega x, this rate of rotation in a plane which is in the board or slide, you can say, is equal to 1 over 2 means half as per definition del W over del Y minus del V over del Z. Now what is del W over del Y and del V over del Z? So in this case so omega z, I am writing it here, omega z is equal to, in this direction means counterclockwise direction, if we are giving this as plus sign, then for clockwise direction we have to give minus sign. and omega z means we are considering a plane which is shown here in xy plane. So what is this angle delta alpha? This was equal to del v over del x. This is given plus sign because here rotation is happening in this direction and here rotation is happening in this direction, means clockwise direction, so we have to give minus sign. So minus del u over del y. So this is the angular change at a point of these two mutually perpendicular lines intersecting at the original point O. We want to know the rate of rotation at point O, and as per definition it is half of that, so it is half of these. So this term omega z is known as rotation, which is equal to average of angle made by the x line and angle made by the y line at that particular point. Similarly, if we want to know the corresponding angular rotation in x direction and y direction, in x direction this will be equal to 1 over 2 del w over del y minus del v over del z, and in omega y means in xz plane, so this will be equal to half of del u over del z minus del w over del x. Now once we know these terms, then for three-dimensional flow we can define the rotation with the help of this omega, which is equal to I omega x plus j cap omega y plus k cap omega z, and if we substitute the value of omega x, omega y, omega z in this equation, we will get the net omega of that fluid element having velocity gradient in x direction, y direction, z direction, that is equal to 1 over 2 I cap del w over del y minus del v over del z plus j del u over del z minus del w over del x plus k cap del v over del x minus del u over del y. Now this term, these 1, 2, 3 terms, they are also represented by curl of v. What is curl of v? Delta cross v vector. So this is for sake of simplicity. Sometimes we write that omega is equal to 1 over 2 curl of v. So with the help of vector, sometimes these equations may be written in a simplified manner, but for that we must have some exposure of the vector analysis. Now let's say if we have a polar coordinate. For polar coordinate, this del cross v or curl of v is equal to er cap 1 over r del vz over del theta minus del v theta over del z plus e theta cap del vr over del z minus del vz over del r plus k cap 1 over r del r v theta divided by del r minus 1 over r del vr over del theta. So we have not done this derivation, but we are writing in this format if we have a polar coordinate system. as far as this curl of V is concerned, this may be written in this format also. This thing you have studied in the mathematics also, but for sake of completeness, I am writing here also. Ijk del over del x plus del over del y plus del over del z, and for Cartesian coordinate system, it is u, v, w. If we expand it, we will get this term, which is equal to omega, means rate of rotation of the fluid element. Now this direction of the vector cross product is determined by this right hand side rule. If this is B vector in our right hand side and this is A vector, so what is A cross B? This A cross B will be represented by the direction of the thumb, and that is equal to C. So C is the A cross B. So because it is a vector, so we need to find out the direction also. Now we have defined some more terms, like we have defined vorticity. This vorticity is basically one kind of rotation, but that is equal to twice of omega. So if twice of omega is written as, then this is term called Chi. This is called, in nomenclature, this is called zeta. This is zeta. In Roman nomenclature, this is called zeta. So zeta is twice of omega. So rate, this vorticity is nothing but it is kind of rotation, but we want to submerge this 1 over 2. That's why we have defined this term vorticity. So vorticity for the cylindrical coordinate can be written like this. But for two-dimensional flow in cylindrical coordinates, where we have a flow only in r theta direction, r theta plane, means Ez is perpendicular to that plane. So in r theta, we have only this component. So if we have two-dimensional flow in r theta plane, then this zeta, what is zeta? It is vorticity. And what is vorticity? It is twice of rotation. So this is equal to 1 over r del over del r u theta minus del u r over del theta and k cap. Right. So please remember these things, because these will be helpful in solving some numericals. The circulation. Now we are defining another term. Circulation. This circulation is defined as, and this is denoted by gamma. This gamma is line integral of, this is for closed curve. Suppose you have a fluid flow in which we have this closed curve. Then for this closed curve, suppose here you have the velocity vector, and this is the position of this displacement ds, then v dot ds, and line integral of v dot ds is called circulation. Now this circulation can be calculated for different type of numericals, and we will relate this circulation to vorticity and rotation and its usefulness. So in this small video we have learned that if fluid is flowing in some flow field where velocity may be function of, may be constant, may be function of x and y, may be function of x, y, z, but here we have not considered the function of t, means it is a steady flow. In that case, what happens to fluid particles as it goes through that flow field? And we have evaluated different type of deformation when it is passed through these different type of flow field, and we have related the linear strain rate, the rate of rotation, and the shear strain rate to the corresponding velocity gradient. And then we discussed about the vorticity and circulation. Thank you.